Welcome to class students. In this video we are going to discuss tasks and functions, how to use in Verilog, how to write and how to use invoke tasks and functions. And also we concentrate on what is the difference between a task and a function. Functions and task differences if you observe. A function can enable another function but not another task. A task can enable other tasks and functions. Function always execute in zero simulation time. Task may execute in non-zero simulation time. So it means that it takes some time to execute. Here instantaneously function executes within no time. Functions must not contain any delay, event or timing control statements, whereas in tasks it may contain delay, event or timing control statements. Functions must have at least one input argument. They can have more than one input argument also, at least one input argument. Task may have 0 or more arguments of type input, output or in-out. Functions always return a single value. They cannot have output or in-out arguments. Tasks do not return with a value but can pass multiple values through output and in-out arguments. Tasks are declared with keyword task and end task. Task must be used if any one of the following condition is true for the procedure. If there are delay, timing or event control constructs in the procedure has 0 or more than 1 output arguments, the procedure has no input arguments. So when we need to use task? So there are 3 conditions. If delays are included, timing and event controls are included, if a procedure has no argument, input arguments, or it has more than 1 output arguments, in that case we need to use task. We'll see an example. Consider a task called bitwise underscore operation, OPER, bitwise operation, which computes the bitwise and bitwise or bitwise XOR operations of two 16-bit numbers. The two 16-bit numbers A and B are inputs and 3 outputs are 16-bit numbers, that is represented as AB underscore and AB OR operation, AB XOR operation with these identifiers. A parameter delay is also used in the task. So module name given as operation, parameter we have defined delay as 10, register 15 down to 0, A and B we are defined of size 16-bit each, and outputs register 15:0 AB and AB or AB XOR. Within always statement, whenever A or B value changes, this always construct is selected, and within always statement we are using a task with a name bitwise operation, OPER. AB and AB or AB XOR are the 3 outputs generated, we are expected to generate from task, and A and B are the inputs. So whenever A or B value changes, this bitwise task is selected, and how this task is implemented we'll see in next slide. You can observe here a task bitwise operator is defined. The name given for this task is bitwise operator. Output 15:0 AB and AB or AB XOR. So within task we are written three outputs which performs AND, OR and XOR operation on input operands A and B. A and B are also of size 16-bit. Output size is also 16-bit in the declaration part. So once you define output and input, here you can observe that there are multiple inputs and there are also multiple outputs we have defined in task. So this particular task can return three outputs, AB AND, AB OR, AB XOR. Exclusive return statement we are not writing within the task as we have seen earlier. Begin, which indicates start of the task block. End task, which indicates end of the block. This end task statement, and begin and end act as open brace and closing brace for this task. Here one more observation, delays are included as part of coding. So delay in the code you are defined as 10, hash delay corresponds to hash 10, hash 10 time units. Delay can be included as part of or within the task, that is allowed, but delays cannot be included in function. AB and operation A and B, A or B, A XOR B, we are assigning to corresponding output variables. So when these values are computed from task, wherever this bitwise operation is called, first we are written AND or XOR outputs followed by two inputs A and B. So values that are supplied in, you can observe here, values that are supplied, first three are outputs and then two inputs. The values A and B will map to the A and B defined in a task. AB and AB or AB XOR, which are written in uppercase letters, those are mapped to AB and AB or AB XOR defined in task. So when the values that are computed will be available with these actual signals or registers that we have defined here. So the complete code is not there, partial code is there. We are concentrating on how to write tasks in Verilog. In the above task, okay, the code that we have analyzed, the input values passed to the task are A and B. Hence, when the task is entered, within the task, those A and B values are mapped with lowercase a and b that we have defined in task. A is assigned with A, B is assigned with B. So, lowercase a and b will take values from the always block where we have invoked task. The three output values are computed after a delay. This delay is specified by the parameter delay, which we have defined in code as 10 units for this example. When the task is completed, the output values are passed back to the calling output arguments. Therefore, AB and which we have defined in calling argument is assigned with this value computed here with the lowercase we are assigned for output. Those are assigned to the actual calling arguments when task is completed. We have seen first example, we will see task definition using ANSI style of argument declaration. So the only task block, if you observe, output 15:0 AB and AB or AB XOR, input 15:0 A comma B. So this ANSI style of declaration in task is also supported. Okay. You can observe here. So the output port declaration, the outputs first AB and or XOR, then followed by inputs A and B for this bitwise offer. Begin hash delay, the logic block remains same. AB and after delay and or XOR are computed. When the task is completed, these values are available and these are mapped to the calling variables. Define a module that contains the task asymmetric sequence. We'll see next example. Okay. In the previous example, we can use the regular style of declaration for declaration within the task. Also, we can use ANSI style of argument declaration. Both are allowed. So we have seen that. In the next example, we are generating, we are defining a module that contains task asymmetric sequence. We'll see module sequence, register clock, initialize sequence, invoke task init sequence. So one task for initialization. So since only one statement, no need to write begin and end. So it is also a partial code, entire block is not written. We have to concentrate on how tasks are written in Verilog. So init sequence is one of the tasks. Next, always begin asymmetric sequence. Asymmetric sequence is one more task where we are generating a clock. When you call init sequence, initialize sequence, inside initial statement, it will invoke init sequence and clock will be assigned with value 0. Clock will be assigned with value. You can observe here, when this init sequence is called, clock will get value 0. When asymmetric sequence, one more task is called within always. So this particular always block, when asymmetric sequence is called, invoked, in that case you can observe that initial value of clock is 0. Initial value is 0. For 12 time units, it remains 0, 12. Then clock will get value 0 in asymmetric sequence. Okay, and that remains till next statement is evaluated. It takes additional 5 time units. 5 means 12 plus 5, 17. Till 17, value remains 0. At 17, clock value will become 1. And this remains for 3 time units. So 3 time units it remains 1. So at time 20, value becomes 0. For next 10 time units, value remains 0. So at time 30, again the clock value will become 1. So here we have generated an output sequence, output like this. Asymmetric. Asymmetric means we are generating based on our requirement. This we can call it as, for shorter duration it is 1, means pulse is generated. Based on our requirement of the coding, we can able to generate this clock output. One more time, we'll see the same example. You can observe module sequence, we have defined clock as a register. Whenever you call init sequence, you are initializing clock to 0. And within always statement, you are calling one more task, asymmetric sequence. Based on the statements that we have written, the clock values are updated. So you can observe that we can able to generate asymmetric sequence, that is clock values are changing from 0 to 1 at different instances of simulation timings. Thank you students, we will continue in next class.